All right, so yeah, I just looked at all the quizzes and I have had some concerns, so I want to go over it again. So let me just go ahead and share my screen. So let's put these side by side again. So I know we have a lot of different tests that I'm throwing at you. One thing I want to bring up among some of the things is that I saw some people using tests that I haven't really gone over yet, which is fine. You're certainly allowed to do that, but I don't think in any of those cases they were used properly. So, yeah, you're more than welcome to use things that are out there, whether or not I've explicitly gone over them. But one thing that is kind of falls into the background, what I feel with these sequence and series tests is that all these tests come with conditions, so you can't just use them. You got to be very careful with how you're using. Because, for example, I saw a lot of instances where people were, they were applying a test, but because you missed one requirement of those tests, or you applied it wrong, basically you ended up coming up with the wrong conclusion. So let's go ahead and go over these. So this first one, A, that one diverges, and I saw a lot of people doing the comparison tests, like I said, are very powerful, and I think they do a lot of things well. The direct comparison test, though, is actually it's easy for that one to fall apart. And what I mean by that is, so on my solution here, I started out trying to use the direct comparison test, but it doesn't really work because I am setting my goal as, I want to compare this to 1 over radical n, which those of you who went the direct comparison test route, had that as the series you're going to compare to was 1 over radical n. Some people called it radical n over n, which is fine, but you might as well just simplify it. You can call it just 1 over radical n. And maybe I should ask this, just to make sure that we kind of understand why, and not just see that it works after the fact. Why is 1 over radical n a good series to use for the comparison test? Why not 1 over n? Why not some other power on n?
It's just a guess, but is it because you can't justify that it's bigger or smaller?
Well, that's why the direct comparison test won't work.
It's just isn't this just the order of the whole term itself? Like the top one is half, the bottom one is 1.
Yeah, and that's exactly why I'm choosing 1 over radical n. So greatest power on n in the numerator is 1/2 because of the square root, and the greatest power on n in the denominator is 1. So basically what I would like to do, I mean, I kind of have this intuitive sense, and I suspect that many of you do too, is that, as n gets really large, that 3 underneath the square root is going to get overwhelmed. That 6 in the denominator is going to get overwhelmed. So hopefully you kind of have this sense that as n gets really large, this sequence is going to, more closely resemble, 2 over radical n. And really 2 over radical n is going to, if 1 over radical n converges, then so will it's double. So might as well just compare it to 1 over radical n, but 2 over radical n would get you the same conclusion. But the reason the direct comparison test doesn't work is, all right, I'm going to compare this with 1 over radical n. I know that series diverges. But I cannot, if you look at the string of inequalities here, starts off fine. I have 2 times radical n plus 3 over n plus 6. I know that removing that 3 from the numerator under the square root will make the series even smaller. I know that cutting it in half will make it even smaller again. But, let's say I try to go ahead and plug in my drawing tablet here. The reason that I don't think direct comparison is going to work very well is this. Say I try to put this in here, radical n over n. I don't think I can say that anymore. I don't think that one's true. Because when I take away the plus 6 from the denominator there, I've made the denominator smaller, which means this thing on the right will actually end up being larger. So because of that, I kind of hit a dead end with the direct comparison test. The good news is the limit comparison test, I think it's a little more versatile. I'm not gonna get hindered by that kind of occurrence. So I have my known sequence, or my given sequence, which is a sub n. B sub n is the one I want to compare it to, because I know for a fact that the sum of 1 over radical n diverges. So if I can get some kind of positive limit out of this, then I know I've shown they kind of share the same fate. So the ratio of those limits ends up being 2, and that's all I need. Since the limit comparison test gave me a positive finite real number, then I know those 2 series basically, they either both converge or they both diverge, and I know that the one I brought in diverges. I think limit comparison test is probably the best way to go after that one. By no means do I think it's the only way. I saw some people try to use the integral test there, which it'll probably work. I think it's I think this way is more direct. I actually don't think I saw anybody do the integral correct. I think it gets it's deceptively complicated. The next one, B. You know what? This one's out of date because this, this won't work. So, and I'm kind of glad this happened, but this direct comparison test doesn't actually, this is completely wrong. And the reason it's completely wrong is this. So I want to compare with 1 over n. So I need to have a series that's bigger than 1 over n. And from the very start here, this is false already. So, and, just try some values of n and to see that this is not actually true. But another way to look at it is this. On the left, the denominator is larger. And that's the only thing that's different. So the thing on the left is going to have to be smaller. So I actually need to make sure that I posted the solution to this on Canvas. I need to make sure I posted the updated version because this one's not actually true. But if I do limit comparison with the same series with this, then you'll get a positive, I think you'll get a limit of 1, which is enough to tell you that since this series diverges, so does the one I gave you. So I'm really trying to go over these in pretty good detail, but please ask me questions. I mean, I'm seeing some concerning things on the quizzes, and yeah, I really want to help you all get these things kind of cleared up before the test, which is a week from tonight. So if you have questions, please ask me. All right, C. I think this one is a really good candidate for integral test. And this is one of the reasons I brought up, if you're going to bring in tests that I haven't showed you how to use yet, that's fine, but make sure they're going to be useful. I saw some people try the ratio test, which is not something we've gone over. We'll go over it tonight, but the ratio test doesn't actually get you a good conclusion for this. And I'll go into some more detail why that wouldn't help you. But yeah, the integral test is, I think, is the more direct way to get here. So if you just integrate this continuous function, you'll get a number 1/2e squared. So that means your series converges. For D, what is the series there? Okay, let's limit comparison test again. So hopefully you're seeing how useful these comparison tests are. Based on the quizzes I just looked at, I think the roadblock for a lot of you is choosing the series that we want to compare to. So if we look at D, and I have a rational function here, so it really actually doesn't even need to be a rational function because A wasn't. So really, I can just look at the greatest power of n in both the numerator and denominator. So for D, numerator has the greatest power of n being 1, and denominator, that power is 3. So comparing this with 1/n squared, or if you build it down from n/n cubed, basically I need to have a difference of powers of n. I need the denominator to have 2 greater orders on n.
So would 1/n, like n to the greatest power, always be a good point for comparison?
Not 1/. So I think what you said and what you meant might be 2 different things, because the greatest power on D here would be 1/n cubed. And really, it's not about the greatest power, it's about the difference. The difference in the greatest power in the numerator and the greatest power in the denominator. For example, like let's say you decided to compare with 1/n cubed. So I'll replace this n squared down here with n cubed. Then this limit will actually end up being infinity, which is actually doesn't help you with the comparison tests, with the limit comparison test. For the limit comparison test to tell me anything, I need that limit to be greater than 0, but also finite. So, and this is another thing I wanted to get into because I saw a couple instances of this on the quiz that was due today. So let's say you try 1/n cubed, you're going to get infinity, which doesn't give you anything from this test. On the other hand, if you try 1/n, and let's say you try 1/n, so I will erase what I have here. If you try 1/n, then you are going to get a limit of 0. So the limit exists, but that actually doesn't help us for this test. I need my limit to be positive. And here's why in this instance, here's why knowing how these tests work and really understanding them is crucial. Let's say you get the limit of 0 and you think that, oh, that means that these series do the same thing. And since I know 1/n diverges, then so does the one I gave you. So in that case, you not understanding how the test works and how to apply it, it'll give you the wrong information, because this series actually converges because it behaves like 1/n squared. And the very last one, alternating series test will give you what you want to know, but you're actually better off. I'm not better off, but first of all, the good news is the alternating series test, those of you who used it and said that this series diverges, that's totally fine. That's perfect. Another way to look at this is that there is no limit here. So as I let n get very large, that alternating term will just oscillate between 1 and -1 infinitely. But the rest of this, n over n to the 7, this is going to go to this. Because basically n over n plus 7, that is going to, that portion of this will just go to 1. So then you have the limit of this, which doesn't exist because it's just going to oscillate between two real numbers and never settle on one of them. One thing I also saw a lot of that I want to address is this. So if this looks familiar to you, please don't feel like I'm singling you out because I did see this quite a few times. The limit this is equal to this, -1 to the infinity times infinity over infinity plus 7. Which, you know, there's a reason why we're doing improper integrals, that when you're dealing with infinity, you got to use a limit. You can't just, basically, you can't treat infinity like it's a number and plug it in for variables. But that limit ends up being 1, which is why the series diverges. So you probably don't want to hear me repeat myself any more than I want to repeat myself, but if you need help on this, please let me know. It is literally my job. Please ask me. I will help you however I can. Yeah, the second test is coming quickly, and you know, we're not even quite halfway through this chapter yet, and yeah, it's really good for all of us if we get a handle on these things.
Can you go through the limit test one more time for the last one? That, like, it's a bit, I tried to apply it, but then I felt like I cannot apply it. I cannot take a limit test.
For D or for E?
For E.
I don't, when you say the limit test,
I mean, like, you know, you're taking the,
oh, just finding the limit? Sure.
yeah.
And with this one, it's a little bit, so let's do this. I want the limit as n approaches infinity of -1 to the n times n over n plus 7. So for right now, I'm going to ignore the alternating term. So what I'll do with the rest of this, and you've seen me do this a few times now, basically what I want to do is I want to eliminate all of my positive powers of n. So I'm going to basically divide numerator by n, divide denominator by n. So then I can replace what I started with this, -1 to the n times 1 over 1 plus 7 over n. So hopefully from there, and like I said, we're kind of just, we're leaving the -1 to the n alone right now. But as n gets very large, the 7 over n term is going to tend to 0. So now what I have is -1 to the n times 1 over 1. And that leaves me with this, the limit as n approaches infinity of -1 to the n. So are you okay with those first few steps?
Yeah.
Okay, good. And then from here, there really isn't any more work to show mathematically. From here, it's, and you can kind of make just in plain English justification that, you know, as n increases, and remember, n is only integer value. So as n increases, you know, the sequence here is just going to go -1, 1, -1, 1 indefinitely. So this limit does not exist. And I saw a few people put down that this limit was equal to infinity, which is not true. So that is one way for a limit to fail to exist, is if it just keeps growing and growing, or decreasing and decreasing. This limit doesn't do that.
To some exist. I
What
like
was
it
that, Reyes?
but it converges, right? Because it's like the negative and the positive, it just keeps canceling each other out.
No,
Sort
so two ways to answer that. I am not looking at a series here. I'm only looking at the sequence. So let's go back to what the definition of convergence is. The definition of convergence is, as n gets very large, your terms get closer and closer and closer to one real number. Only one, not two different ones that it kind of goes back and forth between. It has to hone in on one real number, which this sequence does not do. And because the sequence,
okay. So it just keeps going, right? Like if you stop at 1, but there's also like, again, it could be a -1 again, like that.
yeah. So I mean, and the thing is, it's never going to stop, because we have an infinite number of terms. There is no final term to this sequence.
But it should be, like my intuition says that it should be sort of like, there should be an equal distribution of a positive and a negative, right? So
There absolutely will be, but that's not convergence. Even though, yeah, every other term is going to be positive. But that does not mean that that's not convergence.
So if this were a series of partial sums rather than a sequence, it would converge.
No, it would also diverge.
Also.
Because, so let me erase some stuff here, give myself some more room. So let's just look at how the sequence behaves. So sequence and series. This will be -1, 1, -1, 1, -1, 1, and it will continue like that forever. If I take the series, or I guess we can call it sequence of partial sums, then what you're going to have here is this: -1, 0, -1, 0, -1, 0. So in both cases, you have something that, is just going to oscillate back and forth. Neither one of those is going to converge to a single real number. They're definitely not going to get infinitely large or infinitely small, but there are other ways to diverge than just by, growing unbounded.
That makes sense.
Good. And then one last bow I'll put on this is, let's say you have an alternating sequence. Let's say you have an alternating sequence that converges. What's the only thing it can converge to?
Zero.
0, right. So it can't converge to a positive number if half the terms are negative, and vice versa. So the only possible way an alternating sequence can converge is if it tends towards 0. Okay, so before I move on to new stuff, please ask me questions about anything I talked about with our existing tests. So I'm gonna give you 1 or 2 more to think about tonight. Okay, let's go for it. I don't have it. All right, can you all see my screen here?
Yes.
All right, so section 6. I saw people using the ratio and root tests for this quiz, and yeah, that's part of what we're going to be talking today. We're also going to be talking about the idea of absolute convergence. So, based on what we did yesterday, we know that this top series, the harmonic series, diverges, and we know the alternating version of that series converges. And we got that from the alternating series test and a couple of animations and graphs that I showed you yesterday. So based on that fact, everything we've done so far has been either convergent or divergent. Now we're going to bring in one more layer to more specifically describe alternating series in particular. And that idea is absolute convergence. So the way that works is this. Let's say I have some series. And then, so notice the difference between this thing and this thing. So basically, if I have some series, let's say that instead of looking at that series, I want to look at a similar series, except instead of looking at all the terms added together, I'm adding together all the absolute values of the terms. So if I take the absolute value of all the terms and then add that together, if that still converges, that's called absolute convergence. All right, but what happens if this situation, let's say your base series converges, but if you add all the absolute values together, that diverges. That situation is called conditional convergence. Any questions on that definition so far? All right, so let's look at an example. So we've all seen this one before. So really our three options now are this. We either have a sequence or a series that diverges, converges conditionally, or converges absolutely. So this series right here, which we talked about quite a bit last night, what does this one do?
Converge.
It converges, but so based on that, I can do this. I can throw out this choice because I know that under some circumstance it converges. So let me ask you this. Does the series as written converge? So as I gave it to you, does that converge?
That would diverge.
No, this one actually converges. So this is the first example we looked at with the alternating series test. So let's just refresh that. So alternating series test. And I'll have you all remind me. What are the conditions I need to use the alternating series test?
Needs to be decreasing.
Okay. And specifically, what needs to be decreasing?
B of n.
Right. So the non-alternating part, that needs to be decreasing. And 1 over n is certainly decreasing. What else has to be true for alternating series test to be usable?
It needs to be positive.
Yep. And that's the non-alternating part. And what's our third condition?
It needs to be alternating.
Yeah, it needs to be alternating. Which that's what the negative 1 to the n is going to do. It's going to alternate every other term is going to be positive. So we meet all the conditions. So I'm allowed to use the test. So how do I use it? What am I really looking at?
The limit of 1 over n.
Right. So I want to know the limit of the non-alternating part. And that limit is equal to 0. Therefore, this series converges. So I have an alternating series that converges. So that means it converges conditionally, but it still might converge absolutely. So I also want to look at this. The absolute value of negative 1 to the n over n. So is there another way to rewrite this series?
Just 1 over n.
Yeah, it's just 1 over n. So basically, that alternating term there, since that alternating term is either it's 1, negative 1, 1, negative 1, taking the absolute value is just going to make it always 1. What does this series do?
That one diverges.
This one diverges. So, because the series as written converges, but the absolute value diverges, is that conditional convergence or absolute convergence?
Conditional convergence.
That's conditional. So basically, the only way this series converges is if I have it alternate. If I take away the alternation, it fails to converge. So any questions on this first one here? All right, moving on. All right, so let's go ahead and write down our options again. So how do we get started?
You see if it diverges or converges.
Okay, so as written, does this series converge or diverge?
I think it converges.
It converges. So this one converges, and I will just state this, but if anybody wants me to verify it and write it out, I'll tell you the alternating series test is totally fair here, and it will show you that that series converges. So we can throw out divergence. So in order to narrow it down, so it at least converges conditionally, but now we got to see if it converges absolutely as well. So what else do we need to look at?
The absolute value of it.
Right. So I'm going to take the absolute value of all these terms. And that absolute value is basically going to take all the negative terms in this sequence and make them positive, so the alternation goes away. What does this series do?
Converges.
That converges, and how do we know that it does?
The P series test.
Yep, converges by P series. Because P is equal to 2, which is greater than 1. So that means that this series absolutely converges. Any questions before I move to the next one? Right. How about this one? So what should we look at to start?
If it converges, it diverges.
Okay.
And I
So
think it
as written,
converges.
what was that, Jacob?
I think it converges.
And you're right, it does. So we can throw out diversion again. So one thing we should look at here is, conditionally converges, this idea right here, this only applies to alternating series. Is the series I gave you an alternating series?
Yeah.
It's actually not, and I admit I threw this one in here to trick you. So if you get out a calculator, make sure you're in radian mode, but if you take the first few terms here, cosine, and just numerators, cosine 1, cosine 2, cosine 3, and so on, I believe you will get that cosine of 1 is positive. Cosine of 2 should be negative. Cosine of 3, I think, is also negative. Cosine of 4 is negative. Cosine of 5 is going to be positive. So basically what you have is you have a sequence that has some positive terms, some negative terms, but it's not alternating. So alternating doesn't just mean that some terms are positive, some terms are negative. It means that successive terms are always going to have opposite signs, which in this case they're not. So because of that, this actually cannot converge conditionally. So since that idea of conditional convergence is only makes sense for alternating series, then we have two options: diverges or converges absolutely. And maybe we kind of jumped the gun here, but that's okay. Now we can go back and justify it. How do I know that this series converges?
Squeeze there.
The squeeze theorem. So if we're going to use the squeeze theorem, we need to basically, what's our series, what's our sequence that's always larger, and what's our sequence that's always smaller?
It's -1 and 1. Negative 1 over n squared.
Yeah, you need the over n squared. But keep in mind that since cosine, cosine always oscillates between -1 and 1. So if I have -1 over n squared, that'll always be less than or equal to cosine n over n squared. And similarly, positive 1 over n squared will always be the maximum. So squeeze theorem says I get to just look at the limits of these bookend sequences. So that means that this limit has, and actually I really should be looking at their series. And in that case, it's not the sequences that help me, it's that knowing that the one on the left, the series on the left and the series on the right, those both converge because of the p-series. So the one in the middle has to as well. All right, any questions on this one? Are we okay with why I am saying this is not an alternating series? Okay. Moving on, how about this one here? Before we get too deep in this one, do we even have any intuition about what this thing does? And it's okay if you don't. I'm kind of using this as a segue to jump into our next test here. So next test I want to look at is the ratio test. And the way the ratio test works is this. Really, its purpose is this. I want to, a series that I know a lot about that I can really easily characterize as a geometric series. So my hope is that if I'm looking at some, more general series, that eventually it'll mimic a geometric series. And remember that a geometric series, the only thing it needs to make it a geometric series is that there's some common number, that common ratio, that if I multiply it by one term, I'll always get the next. So I can't rely on, all series to do that all the time, but maybe I can rely on my series that I care about to do that, as n gets really big. So that's what I'm going to do with this ratio test. I'm looking at this limit here. So as n gets really, really big, I want to take the ratio of one term to the one that came before it. And if I get a limit for that, then basically what I've shown is that, my sequence, my series is not geometric, but it acts enough like one that I can draw some conclusions. So we're treating this like a geometric series. So because of that, what values of L are going to make this, are going to give me convergence? What common ratios will make a geometric series converge? So assuming L exists, just like a geometric series, if that limit is less than 1, then that series converges absolutely. If the limit's bigger than 1, the series diverges. And here's the case you don't want to run into. If the limit is equal to 1, then you got nothing. You have to try some other test to figure out whether your series converges or diverges. So this is a test that, hopefully I'm going to kind of show you some good examples for which to use this, but in those examples, in these cases where it works, it's really powerful. It's a really good tool to use. Any questions on any of the conditions so far? Okay, so let's look at the example we just looked at. So don't really know about this one, so I want to look at the ratio test. So I'm going to look at what happens as n gets really big and I divide one term by the one preceding it. And I get something that looks like this. -1 to the n plus 1 times n plus 1 cubed over 3 to the n plus 1 all over just the base sequence, -1 to the n cubed over 3 to the n. So it looks pretty nasty right now, and we got quite a lot of simplification work to do. So the nice thing about the ratio test is if you set it up properly, a lot of things will cancel out. So what are we seeing that I can simplify here? So one thing I'm going to remind you of is to look at your exponent laws. So we're not always going to go this gradually every time, but I know that I can do this. I can pull apart this -1 to the n plus 1 into -1 to the n times -1 to the 1. I don't really want to expand n plus 1 cubed unless I find out that I have to. This becomes 3 to the n times 3 all over -1 to the n times n cubed over 3 to the n. So now that I've split these things apart, we can see that this will cancel this. 3 to the n cancels 3 to the n. So now what I'm left with is, and I'm only looking at absolute values, so that -1 is not really going to have any effect. So what I really have now is n plus 1 cubed over 3n cubed. I'll go ahead and rewrite this over here. How can I evaluate this limit from here?
Could you divide or multiply the top and the bottom by 1 over n to the third?
Yep. So even though I have this, I have a n plus 1, that whole quantity cubed, I can still, basically, I'm going to re-express it this way. So I have in the numerator n plus 1 to the third times 1 over n. I'm going to write it like that, all to the third over, and this just becomes 3. So now that I have these two brackets in the numerator, both raised to the third power, I can basically do this. One over n times n plus 1, all to the third, over 3. And now basically I can do all those simplifications inside the parentheses. So then that becomes 1 plus 1 over n cubed over 3 And as n gets really large, that 1 over n will go to 0. So this limit becomes 1/3. So that limit is 1/3. So what does that mean about this series? What conclusion can I draw from here?
Convert.
Converges. Can I be more specific than that?
Condition.
Not conditionally. It's actually absolutely.
Not conditionally.
Yeah. So the ratio test actually doesn't have a way to show you conditional convergence. It either shows you absolute convergence, divergence, or in that bad case where the limit lands right on the boundary of 1, you draw no conclusion. You have to try something else. So any questions about this first usage of the ratio test? All right, let's keep on going. So this is a series I think we've looked at before, but we looked at it in kind of a strange way. The ratio test actually makes this a lot easier to think about. So I want to look at the limit as n approaches infinity of same ratio, a sub n plus 1 over a sub n. And then it's just a matter of, basically, I'm going to start out with this compound fraction, n plus 1, raised to the n plus 1 over n plus 1 factorial, all over n to the n over n factorial. And this is maybe for now a little mysterious on how things cancel. So let's start with the factorials. So let's just do a concrete example up here. If I wrote down 6 factorial, how would I compute that?
Six times 120.
6 what?
720.
How'd you get 720?
It'd be 6 times 5 times 4.
Yep.
And so on.
So yeah, absolutely. So yeah, it's absolutely equal to 720, but we're going to try to generalize this. So let's be clear about where that thing comes from. But let's say, how does that relate to 7 factorial? Clearly, that's just equal to 7 times 6 times 5 and all the way down. But hopefully it's clear that, contained in this calculation for 7 factorial is 6 factorial. So I could also re-express 7 factorial as 7 times 6 factorial. So because of that, I eventually want to cancel out these as much of this as I can. So what I would like to do is this. I want to rewrite n plus 1 factorial, and I'll leave everything else the same. So n plus 1 to the n plus 1 over n factorial times n plus 1 all over n to the n times n factorial. And I'm going to stop there because just from experience, I think this can be a bit mysterious. So ask me some questions, or maybe just take a moment to absorb why I'm able to make that rewrite. But from here, now I essentially have no factorials left. I've canceled them out. And here's something else I'm going to do. Everything I'm dealing with right now is positive. So the absolute value arguments the absolute value operator isn't really doing anything for me, so I'm just going to leave it off. So now I have n plus 1 raised to the power of n plus 1 over n to the n times n plus 1. So where can I go from here? That should not be there. Oh, yeah, should. Okay.
When did you split up n plus 1?
Which one? That shows up a few different places.
Oh, sorry, the top one.
Okay. How so?
Okay. Oh, wait. You could do n plus 1 to the n power and then times n plus 1 to the first power.
Good. So n plus 1 to the n times n plus 1. And that's actually going to make something really easy for me. N to the n times n plus 1. All right, so where can I go from here?
Are you allowed to multiply each one by 1 over n to the n? Or can you not do that?
Yeah, we can do that. How is that going to? So basically the same thing as before. Denominator is a little easier to deal with. That is just going to become, you know, n over n to the n. Other ones going to become n over n plus 1 over n to the n. But here's the problem. This ends up being 1 over 1. So our limit is 1. So what does that tell us about this series?
Nothing.
Nothing. So, and this is kind of one of the dangers of this test is that sometimes you can just set this up where this doesn't work. And there's kind of a good news, bad news situation here. The good news is, you know, this isn't like the direct comparison or limit comparison test. There's no real decision to be made about what other series to bring in. Really, the way I set this up has the only thing you really have to look at is how the series is defined. And then really you're just playing with the indices. The bad news is if it doesn't work, there's no real way to make it work. You can't like bring something else in to somehow get a conclusion. So yeah, this one here doesn't really work. We have previously showed that it converges. And because all the terms are positive, it converges absolutely. But the ratio test actually wouldn't help us here. Any questions about what we come up with or how we got that conclusion? All right. Next test I want to look at is the root test. So basically what I'm looking at here is I'm going to take the nth root of the absolute value of my sequence and then let n grow. Let n go to infinity and see what I come up with. And assuming that limit L exists, hopefully this looks familiar, basically the same criteria apply. So if L is less than 1, then you have absolute convergence. If L is greater than 1, you have divergence, and if it lands on 1, then you get no conclusion. So again, I saw people trying to use this on the quiz, and I don't believe it was used correctly or in a way that I think, in fact, I think both the times I saw L equals 1, which doesn't give you anything. So let's look at this one here. So basically I have some rational function, but that rational function is raised to the power of n. So if it was just 2n plus 3 over 3n plus 2, and that was it, this would be pretty easy to analyze. But because of this power here, this is basically a big giveaway that I want to use the root test. And when I set this up, it'll probably become really clear why. So I want the limit as n approaches infinity of the nth root of the absolute value of a sub n. Or if you prefer, the absolute value of a plus n, or a sub n raised to the power of 1 over n. So both equivalent. So that's what I'm looking at. Let's go ahead and substitute in the absolute value of a sub n. So this would be the absolute value of 2n plus 3 over 3n plus 2. All right, does anybody see what happens as I set this up? How can I re-express this?
You can get rid of the nth root and the to the power of n.
Right, those are just going to cancel each other out. In fact, one thing I should probably do before that is, since n is only positive, then these absolute value bars aren't really making a difference. So first step I'll take is this. And then, yeah, Rios is that, or I think that was Rios, is absolutely right that the nth root and the nth power will annihilate each other. So I just have this. And what does this limit equal to?
Isn't it 2/3?
Yep, it's 2/3. So what does that mean about this series?
It converges absolutely.
It converges absolutely. Just to be really clear about that, that's because 2/3 is less than 1. So this series right here converges absolutely. All right, any questions there? All right, how about this one here? So let's go ahead and set this up using the root test again. I'm going to ignore the absolute values because everything is going to be positive valued again. So in this case, we're probably going to do some manipulations to keep simplifying. So what's something I can do here to help me keep simplifying?
Could you pull out n?
Which one?
Could you pull up the n from both powers? Like pull out the to the power of n on the first one, and then the.
So let's do that slowly because one thing I wanted to bring up before is just, on the quiz, I forgot to bring this up, was, and I saw this on the previous two actually. Most of you need to be justifying basically your conclusions a little more slowly. So for example, I saw when people were using limit comparison and direct comparison test, just basically in one shot would say, all right, this sequence is less than this one, when really all at once it's not obvious. Maybe I'll go into more detail about that if we have time at the end, but yeah, they're basically, so long as it's all correct, you can't really give me too much information. So if I basically think of this nth root applied to both numerator and denominator, then the numerator is clearly just going to become n. And now I'll worry about this. And here, I think it might be more valuable to look at, instead of looking at the nth root, let's think of it as the power of 1 over n. Because if I treat this as the power of 1 over n, what happens to that denominator? Basically, what's my new power on 3?
One over n plus 2.
1 over n plus 2. And then from there, I can use my exponent laws to pull this apart. So this becomes 3 to the 1 over n times 3 to the 2. So the limit as n approaches infinity of n over 9 times 3 to the 1 over n.
Infinity, right?
Yep, this is going to go to infinity. Because as n goes to infinity, what's going to happen to 3 to the 1 over n?
Wouldn't it be 3 to the 0?
It would trend towards 3 to the 0, which is 1. So this basically is going to go to infinity. And what does that mean?
Diverges.
Yes, series diverges. All right. Anything you want to talk about with this one? All right. How about this one? So let's go ahead and set up root test. This time, the absolute value is actually very important. So the nth root of the absolute value of negative 12 to the n over n. All right, so now I'll let you all take over. What do I do from here?
Could you change it into negative 12 over the nth root of n?
There's probably something I should do first. So
Oh, change it to it's positive 12.
yeah, so, and I'll do this, I won't always do this slowly, but we can do this now. This negative 12 to the n, I can treat this like this. The absolute value of 12 to the n times negative 1 to the n over n. And because of that, the absolute value is just going to cancel out the alternation. So then what I really have is the nth root of 12 to the n over n. So now I'll go with that suggestion before that. And what I get here is, yeah, this ends up being 12 to the n over n over n to the 1 over n. So 12 to the n over n just becomes 12. And one thing I will give you for free that you can use without really having to justify it is this fact here. As n goes to infinity, this limit here, n to the power of 1 over n is equal to 1. So maybe that's intuitive, but I think it's actually, it can cause a little problem, because we know that as n gets really large, basically the n that's in the base is going to get very large, and the exponent is going to trend towards 0. So really what ends up happening is it's more significant that exponent is going towards 0, so we have this limit being 1. So really what we have here is limit is 12 over 1, 12. So this series here diverges. And I am guessing some of you probably saw that coming. You know that the series of 1 over n diverges. And this one's just, the values are going to get even further away from 0 because of that negative 12 to the n. Any questions here? All right. So section 7 is pretty short. So let's go ahead and do that before we break for a bit. So I've shown you an awful lot of tests. So really what I just want to do is 7, and we won't necessarily go into huge detail for all of these, but basically kind of want to get an idea of how to choose what test in a given situation. So let's just make a list here. So what tests do we have so far? Or what methods do we have for analyzing sequences in series?
We have the squeeze.
Okay, so we got the squeeze there. What else?
We have the direct comparison test.
Okay, so I got direct comparison.
And then
Also-
the limit comparison.
Yep. And it's kind of been a while, but what's the very first one that we talked about?
Would it be p-series?
We have talked about p-series, but there's one that we probably went over maybe in the first or second section, probably a week or two ago. I'm going to put at the top, the divergence theorem. And this one, it's one of those things that, it's very quick, so I think it's usually worth doing, because if it gives you a conclusion, you're done. So just a reminder, what does the divergence theorem say? Basically, if you have this, if the limit as n approaches infinity of a sub n is not equal to 0, then this series diverges. So if the sequence does anything other than converge to 0, the series can't converge. So that's a quick test that you can usually do. That might save you some effort going forward. So we got divergence theorem, squeeze theorem, the two comparison tests, P series. What else have we done?
Geometric.
Yep, geometric series. I can think of at least 3 others that we can put here.
Alternating.
Yep, alternating series test. All right. What else?
And then the ratio and root test.
Yeah. So those should be hopefully pretty fresh in your mind. And I think that's it, unless I'm forgetting anything. But really, a lot that we've looked at so far. So I think that's a comprehensive list of the things we've looked at so far. So let's go ahead and let's look at a few examples and try to categorize, you know, what's the best test to use for these situations. So this one here, what is a good series to use or a good test to use to figure out the series here?
Would it be the divergence?
Okay, so why do you say divergence test?
Because it just seems pretty simple to like just find the limit of that series.
When you say the limit of that, let's be specific. The limit of what limit are you looking at?
n-1 over 2n plus 1.
Right, so the limit of the sequence itself, right? So what is this limit?
One half.
Yeah, this limit is 1/2. And I'll go ahead and do one manipulation to this. 1 minus 1 over n over 2 plus 1 over n, which is equal to 1/2. So why does that tell us everything we need to know?
This is not 0.
All right, that's all that matters. This is not 0. Therefore, the series that's associated with that sequence, you know, can't possibly converge. So that's kind of why I bring up the divergence test and why it's so powerful, is because, you know, it only takes a few seconds really to apply. And usually you don't even have to really write anything down. I mean, if you're going to use it to prove something, you should write something down, but I'm guessing more than a couple of you can look at this sequence n minus 1 over 2n plus 1 and see that the limit is 1/2 without doing too much. That is, I am not giving you permission not to show work, but definitely you can do some of the preliminary work in your head. So any questions on that first one? And just to be really clear, what happens what if we look at that limit and the limit is 0? What does that tell us? So let's say I look at this limit. What does that tell us about this series?
It converges.
It actually doesn't tell you that. So, in fact, the one example I can give you is this here, because that limit is definitely 0, but we know that that series diverges. So that's kind of the trade-off of the divergence theorem, the divergence test, is that if it gives you conclusion, it's, you know, it's you're done, but that is the only conclusion it can give you. It doesn't tell you anything about convergence. It either tells you that a series diverges or you need to try something else. All right, how about this one here? There's a good test used for this one.
Maybe comparison.
Okay, so I'm hearing comparison. Which one would you like to try?
Would be 1/n.
Okay, so that's the series you want to compare it to, but are you talking about direct comparison test or limit comparison?
Probably limit.
So let's try a limit comparison with 1/n. So the way that works, so actually you tell me the way it works. So I want to try a limit comparison with the series 1/n. So where do I need to go from here?
You would look at the limit of that series over 1/n.
Okay, good. So I want the limit of this quotient here, n cubed plus 1 over all this stuff. All right, so that's a good start. Where can we go from there?
You could multiply the top and the bottom by 1/n.
Okay, multiply top and bottom by 1/n cubed. So that is going to be, I'm going to leave the first n alone and then just introduce this 1/n cubed.
Sorry, I have to let my dogs out.
Oh, it's right. All right.
So it'd be on the bottom, it would be 3.
Yeah, to the bottom first. Yep, 3 plus 4/n plus 2/n cubed. And it's the numerator that's getting kind of strange. So I'll do this. 1/n cubed is the same thing as 1 over the square root of n to the 6th. Is that okay? And the reason I'm doing that is so I can do this. N times n cubed plus 1 all under the radical times the square root of 1/n to the 6th. So what is this limit going to do? I think in the numerator we have an issue because this n on the outside of the radical, that's going to get very large, go to infinity. The inside of the radical is going to go to 0. So I don't think it's clear what the numerator is going to do. So I think we need to backtrack a little bit. I think the limit comparison test is probably the best way to go. I don't know if I'm convinced about 1 over n being the series to compare it with. So one thing I'll remind us of is let's look at the highest power of n in the numerator and the denominator. Denominator is pretty easy. I'm looking at n cubed there. What is the highest power of n in the numerator?
3/2.
3/2. So because of that, what's probably a better test to use, or not a better test, a better series to compare it to?
1 over n cubed.
Not n cubed. So actually, let's kind of build this up. So 1 over n didn't quite work. So let's try instead n to the 3/2 over n cubed. Or equivalently, 1 over n to the 3/2. And like I said before, I think that's one of the big hangups with where a lot of you are with the comparison tests. So I want to make sure that you actually understand why I did this thing here. So now let's set up a new limit that hopefully behaves better for us. So limit of square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2 over 1 over n to the 3/2. So now what we get here is, so denominator will stay 3n cubed plus 4n squared plus 2. This is now going to be, and I'm going to rewrite it a little bit differently. Square root of n cubed times the square root of n cubed plus 1. So now from there, I get this limit. Is it clear yet what this limit is going to come out to be? So I'm going to leave this for, if you want, you can go back and look at these slides and fill in the details, but this limit is going to come out to be 1/3. So because that limit is 1/3, which is positive, what does that mean about this series? So the series that we compared this to, what does that series do? So this converges by p series. So the series that we started with, that one converges as well. All right, let's go ahead and move on to another one here. What test do we think about? I think would be good for this one.
Would direct comparison work?
Direct comparison was, so what would you compare it to?
I don't exactly, I'm always confused by LNs or natural logs, but I'm assuming you could do 1 over n maybe.
Okay, so direct comparison with 1 over n. So what does the series 1 over n do?
That diverges.
That diverges. So then what needs to be the relationship between these two series or these two sequences? Which one needs to be bigger?
Isn't it the left one?
The left one has to be bigger. So now, is this going to be true?
I don't think so.
It's not going to be true. In fact, I keep messing this up, but n equals 1 is going to make this undefined. So that's not going to be true. So direct comparison might be possible, but I certainly can't use it with that series. So is there something else we can try? And one hint I'll give you here, that natural log really makes it hard to compare with anything, because there's not really a p series I can compare it to. So think about the things we usually use with the comparison tests. We usually stick with, p series and geometric series, and that natural log is going to make it really hard for me to choose a good series to compare with. So direct comparison's probably out. Ratio test and root, I mean, there's no roots or no powers here for the root test to help us with. Ratio test probably not going to help. So what's left? So keep in mind that 1 over n natural log of n, this is going to be positive. This is going to be decreasing. So we had a handful of tests that we went over yesterday, that maybe the week before, I think it was yesterday, that deal with sequences that are positive and decreasing. And I think this one right here is, or go ahead, Jacob.
I was gonna say alternating, you need to check those 2 boxes, but I don't
Yeah,
think it's
so
alternating.
it does not alternate, no. So I think this one here would be good for the integral test. This actually is a function that integrates. So here's what I'm going to do. I feel like we're running out of steam. So let's take a break here. If you want, I'm going to leave the details of this integral to you. We can talk about it if you want when we come back. Otherwise, we'll just say that this is a good candidate, or probably the best approach here is the integral test. But I'll leave it at that. I got 7:47. Let's go ahead and come back at 7:57, and we'll finish this up. All right, let's go ahead and keep going. So next example here. What's a good test to apply here?
The alternating series test.
Alternating series test, and that one, I think it's pretty clear why to choose that one, but that's a good idea. So now let's apply it. So you got an alternating series. So if this thing converges, you got to be a little more specific. So the way this series is written, does this converge? So really now what we're looking at is, and I'll leave the details to you to check whether the non-alternating part is positive and decreasing. But if we look at this limit here, what we have is 0 over 1 plus 0. This goes to 0. So we definitely know that our series converges, but then it remains to show how it converges. So does this converge absolutely or convergently, or conditionally? So how can we check that?
We look at the absolute value.
Right. So we look at the absolute value, and really, the only change that is really going to make is the alternation. So we're really looking at this, n cubed over n to the fourth plus 1. So how can we try to figure out the convergence or divergence of this series? Basically, we need a test within this test.
My mind goes straight to comparison test.
Yeah, I mean, comparison tests are really versatile. So comparison test, what do you want to compare it to?
It's either, would it be 1 over n to the fourth, or would it be 1 over n?
Be 1 over n, and here's why. So the reason it's not 1 over n to the fourth is because it's not about what the highest power is on n. It's about the difference in the highest power on n when you look at the numerator denominator. So, and in fact, we can kind of even build up to it. So let's say we built up to it. We can compare this with highest power in the numerator is n cubed. Highest power in the denominator is n to the fourth. So that series is going to be equivalent to this one, 1 over n. So yeah, it's a good comparison, and I'm going to fill in with limit comparison because I don't think direct comparison will work. So if we try to set this up with what we would need is for this to be true, and I don't believe that it is. But really, if you have any doubt, you can go straight to limit comparison. And just look at this, n cubed over n to the 4th plus 1 over 1 over n. And this limit's equal to 1. And since that's positive, that tells me that this series right here diverges. So the absolute value diverges. So does that mean that my alternating series converges conditionally or absolutely?
Conditionally.
That's conditional convergence. Yep.
So I have a quick question.
Go ahead.
So if it was like 2n cubed over n to the 4th, does that change anything or?
No, I mean, if it was 2, then that's just going to make this limit here. That would make the limit equal to 2. And let's just be clear. When I find this limit, what am I looking for? What do I need the limit to be?
Greater than 0?
Just positive, right? So if it's 2, it's going to draw the same conclusion for me.
I mean, like, when we were figuring out which one to compare it to,
Mhm.
if it was 2n to the 3rd over n to the 4th, will we still
Oh, yeah.
can simplify
So,
it
I
to
mean,
1 over n?
you're still going to get a positive limit. So, like, let's say that we arbitrarily decided, let's compare this with 15 over n. Not sure why you would bring in 15, but let's say you did. Then what changes is that going to make? That's going to make this 15 over n, which is going to make this right here multiplied by 15, which is going to make this limit 1 over 15. But that is still positive. So that's why, I mean, a couple ways to look at that. It doesn't really make any, it's not necessary to bring in those multiplied constants, but also if you do, it's not going to change anything. You're still going to get a positive limit, which is all you really needed. Okay, moving on to the next one. How about this one? What's a good test to use?
Would it be, I know it's either the root or the other one we did today.
The ratio test?
Yeah.
So, yeah, this power kind of says, you know, a root would cancel that out. But I don't really have any idea how, you know, this thing right here, that's going to be really, I don't see an obvious relationship there. One thing I'll tell you is that I'm not going to say always, because that's, it's just, those absolutes don't really work for us. But factorial is usually a giveaway. The ratio test is at least worth considering. So let's see what the ratio test tells us. So I'm looking at the absolute value of 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. All right, so from here, how can I continue analyzing this?
You could pull out n factorial out of the denominator of both,
Okay, good.
or out of the top one.
Yep. So now I see that will become n factorial times n plus 1. I will go ahead and also separate this. I'm going to leave off the absolute values because there's nothing negative here to worry about. So usually you'll be able to tell that ratio test is helpful because a lot of this is going to happen. So we got a lot of canceling here. So now what we're really looking at is this limit. The limit as n approaches infinity. 2 over n plus 1. What does this limit equal to?
0.
That's equal to 0. So what does that mean about my series here?
It would converge absolutely.
Yep, it converges absolutely. And that is all because my limit is less than 1. All right. How about this one? Sorry.
The root test.
Yeah, so that power, and really that's the only thing, that's the only place this variable n shows up. So we'll try the root test. So as n approaches infinity, this time I need the absolute value because every term is going to be negative. And something I'm going to do here is this. Since I know that all of these terms, actually, I better not do that. So let's just keep it the way it is. Be a little less confusing. I'm going to rewrite this as the absolute value of 1 over 2 minus 3 to the n raised to the 1 over n. That is not going to do anything to the numerator. Actually, we can just go ahead and evaluate this indirectly because there isn't really much more manipulation to do. What is going to happen to the numerator there?
It's going to be 1.
It's going to be 1. Actually, what's going to, so let's think about it in smaller pieces here. As n gets really large, what's going to happen to 3 to the n?
It's going to approach infinity.
It's going to approach infinity, right? So then what's happening to your denominator?
It's going to get really, really large.
You're going to really, really, really large. So then this is going to go to 0. So this one also converges. Absolutely. Which I'm guessing some of you probably suspected, since my numerator is constant and my denominator is just getting not larger and larger, but it's getting further and further from 0. It's actually getting smaller and smaller without bound. All right, so any questions on any of those? Basically how to choose which test to go with. All right, let's go ahead and get into our last section of the night. So probably good news for, in some of your eyes, that we're not looking at any more. I don't really have any new tests to show you. But now we're going to look at a different kind of series. So these series are called power series. And basically the way they work, or the way they look, is this. So a power series has this form. And now notice, basically, I have two different kinds of unknowns here. So like any other series we've looked at, the variable that kind of governs the series is n. So we have a few different things going on here. So I have these different coefficients, and these are just constants, c sub 0, c sub 1, and so on. But as n increases, basically I have this, list of coefficients that are all indexed by n, so c sub 0, c sub 1, and so on. And then I also have x, that its power is increasing by 1 with each new value of n. So, and this series continues indefinitely. So x is a variable, c sub n are the coefficients. So basically the way that we work with these is, we can analyze these series the way we've analyzed everything else. We can test convergence or divergence, using all the things we've already done. It's just basically we have this extra variable, this new variable x to think about as well. And usually we don't even treat x as a variable. This will make more sense in a bit, but usually we just fix values of x, basically set x equal to some value and look at the way the series behaves for that value of x. So a sum of the power series basically looks like this. You can kind of look at it as it taking a function, basically some function of x. And hopefully you are seeing this as similar to a polynomial. And the key difference being that polynomials do not have an infinite number of terms, but power series do. So let's look at this guy here. I want to know, for what values of x does this thing converge? And this is actually a question that we've asked before, and I'll not remind you of the answer, but it'll probably look familiar at the end here. So I want to, before we start looking at the convergence of this thing, let's write out a few terms. So when n equals 0, I'm going to have 1. X to the 0 is 1. When n equals 1, I'm going to have x to the first power, and then x squared, and then x cubed, and this will continue indefinitely. So hopefully it's kind of looking familiar. So this is a power series, but what other kind of series can I say this is like?
Would it be geometric?
It's geometric, right? What's that common ratio going to be, since we're saying it's a geometric series? And what's our first term? First term's 1. But what's our common ratio going to be?
X.
It's x. So based on that, since we already recognize this geometric series, we should already be able to answer that question. For a geometric series to converge, I need the R value to be between -1 and 1. So that means for this to work, I need x to be between -1 and 1. So that's the answer we're shooting for, but let's say we're looking at a power series that isn't this simple, and it isn't as quick to figure out. So let's look at the ratio test. So the limit as x approaches infinity, or as n approaches infinity, of this ratio, absolute value of a sub n plus 1 over a sub n. So that'll give us x to the n plus 1 over x to the n. Really just comes out to be the absolute value of x. And remember, the ratio test only gives me convergence if the limit is less than 1. So another way to express absolute value of x is less than 1, this is equivalent to that. Basically, the absolute value of x less than 1, that means that x is within 1 unit of the origin. So another way to say that is this, which is the answer we knew we were looking for. So I think I made an animation of this. Let me go look for it. So here's the series we just looked at. And can you also still see my screen?
Yeah, we can see the graph.
Okay, good. So basically what I have here, and we know that the sum of this geometric series, even though we didn't explicitly say it just now, is we know a geometric series converges to basically that sum is 1 over 1 minus x. That just comes from that formula that gives us the sum of a geometric series. And we know that's only going to be true when x is between -1 and 1. So this black line here, the black curve, is that 1 over 1 minus x. And basically this function I'm defining here, I'm letting that variable basically give me how many terms in the power series am I going to get. So when f is equal to 0, all I'm really graphing is y equals 1. If I put in 2 terms, then I get, it's a straight line. I mean, it still doesn't really look like that curve, but basically a power series is going to be a better and better approximation the more terms I put into it. So if I go up to the x squared term, it gets a little closer. And really, if I just do one more, so as you can see, let's just go up to 10. And let's go ahead and capture both ends of it. But remember, this is only convergent when x is between -1 and 1. So, as I go towards the endpoints of that interval, you can see that these things don't really match up that well. But because I know it converges on the interval, I can get really, really close and use, now I have 101 terms in there. And basically I can make these behaviors match up really as close as I want just by adding more terms. All right, let's go ahead and go back to slides. So let's look at another one here. And one thing you're going to get used to is that for looking at these power series, the ratio test is really, far more often than not going to be how we handled these. So remember the ratio test, what is the variable when I set up the ratio test? So the variable I'm using the ratio test is n. It is not x, it is only n. So because of that, I get to treat x as a constant. So this limit is going to be equal to n plus 1 factorial times x to the n plus 1 over n factorial times x to the n. So the x's, all you're going to have left is, actually, let's do the factorials first. So now, here's why it's valuable that I can treat x as a constant. I'm going to pull it outside the limit. So for the ratio test to show me convergence, I guess I need to keep the absolute value right next. It could be negative. For the ratio test to show me convergence, what is this limit? What needs to be true about this limit?
It needs to be less than 1.
It needs to be less than 1. But what is this limit equal to? What's going to happen to n plus 1 as n gets very large?
Doesn't it turn into 1?
No, it's going to be bigger than 1.
Would it be infinite?
Yeah, it becomes infinite. So I'm going to make one more rearrangement here. I know that the absolute value of x, the only way to make this converge is if I keep this inequality true. And I'm going to put a less than or equal to in here just for now, because otherwise this thing won't be true. The only way, basically, and this is basically what I have here is the only way that this is going to converge is if x is equal to 0. Which is kind of a useless power series, because if x is equal to 0, then that means every term in this series is going to be equal to 0. It's not a very interesting series. So let me ask you, is this surprising at all? Based on the way this thing is defined, does it make sense that it only converges if x is equal to 0? And let's take a look at the first few terms here. So when n is equal to 0, 0 factorial is 1. So it starts off okay, but then what's the next term going to be? It's going to be x plus 2x squared plus 3 factorial 6x cubed plus 24x to the 4th. Let's do one more, plus 120x to the 5th. So hopefully by writing out the first few terms there, it becomes clear that, what's going to happen to these coefficients. They're going to get, they're only going to get larger as n grows. So the only way for this sum to converge is if x equals 0 and makes all these coefficients irrelevant. So any questions about that one? Okay. All right. Now, how about this one? So, like usual, I want to set up the ratio test. So x minus 3 to the n plus 1 over n plus 1 over x minus 3 to the n over n. All right, so from here, help me simplify.
On the top term, you could split it up so it's x minus 3 to the power of n and then x plus 3 to the power of 1.
Good. So that allows this to happen. And I'm going to go ahead and start splitting things up because I know that really the x minus 3 doesn't have anything to do with the limit. This limit only really, all that matters for that limit is what happens with n. And I know that this limit needs to be less than 1. What is the limit as n approaches infinity of n over n plus 1?
Would it be 1?
Yep, it's 1. So I'm going to leave out the details for now, but yeah, this right here has a limit of 1. So basically what I have is this. Absolute value of x minus 3 is less than 1. So this, are we okay to, do we know how to remove the absolute value from this, or do we need this illustrated again? Which is fine, I think we've only done that one. But I'll draw a picture up here to show why what I'm about to do is true. So I have the absolute value of x minus 3, which basically means I am comparing the distance from x to 3. And I want that distance to be less than 1. So basically my furthest points out are going to be, so 2 is 1 away from 3, but also so is 4. So another way to express this absolute value of x minus 3 is less than 1 is this. X minus 3, not absolute value, is bigger than -1, but less than 1. But now I can solve this thing, this kind of 3-branch inequality, the way we solve equations. I can just add 3 to not both, but now not both sides, but all the different branches here. And I get 2 is less than x, which is less than 4, which agrees with the number line that I drew up there. So here's what I know so far. When x is between 2 and 4, this power series converges. But remember, what does the ratio test tell you? Like, what do you learn from it if the limit is equal to 1? So remember that the ratio test, if the limit's equal to 1, you don't really get a conclusion. So we know that if x is bigger than 2 and less than 4, we're going to converge. But what we don't know is what happens when x equals 2. So now what we're going to do is this. We're going to let x equal 2 and look at this series. So when x equals 2, we're going to have 2 minus 3 to the n over n. Which is equal to -1 to the n over n. What does this series do?
It converges.
This converges. So now what we know is we test, so the ratio test didn't tell us what happened when x equals 2. So we had to use, let's be really clear about this. What test tells us that this thing converges?
The alternating test.
Yeah, this is the alternating series test. So now what I know is this. I can alter my, I'm going to leave the other one there, but now I know this. I can change the interval to, if x is greater than or equal to 2, it converges. Now we just have to look at 4. So when x is equal to 4, I have this, the series of 4 minus 3 to the n over n. And that's just going to come out to be 1 over n. What does this series do?
Diverges.
That diverges, and by what logic?
Isn't it P series?
Yep, diverges by p series. So because of that, my actual, and this right here is called the interval of convergence. So when x is between 2 and 4, including 2, but not including 4. So any questions on how we found that interval of x values?
Real quick, why do we have to do it for this one and not the other ones?
So let's go back to the other ones. This one here, you know, we got x equals 0. There really are no endpoints to look at. And like, so basically the interval we got was this, was 0 is less than or equal to x, which is less than or equal to 0. I mean, we can investigate that by look at this, the way we characterize this series by looking at the first few terms. What is that sum going to be if x is equal to 0?
1.
It's just going to be equal to 1. So it definitely converges when x is equal to 0. And really, by doing that, you've looked at both endpoints. What happens about the this other one? So let's look at the endpoints here. So if x is equal to -1, then your series ends up being this. And I'll write out the other one too. But what does that top series do?
It alternates.
It alternates between -1 and 1. So what's the series going to do?
Would it be diverge?
Yeah, this one diverges. This other series down here is all of the terms in the sequence are 1. So what does this bottom series do?
Converge.
What was that?
Oh, diverge.
Diverge. So the sequence converges to 1, but that actually means the series diverges. So yeah, we did not look at those, and the reason I I kind of blew past that was we recognize it as geometric series. And for a geometric series, we know that a common ratio of 1 or -1 diverges. But yeah, we definitely could have looked at the endpoints more explicitly there. But for a geometric series, I need to be strictly between -1 and 1. But good question, good catch. All right. How about this strange thing? So it's a much nastier looking series, but if the ratio test does us any favors, hopefully a lot of things cancel. So let's set that up first. I'm going to have -1 to the n plus 1 times x to the 2 times quantity n plus 1 over 2 to the 2 n plus 1 times n plus 1 factorial, that quantity squared, over -1 to the n times x to the 2n over 2 to the 2n times n factorial squared. All right, so let's start breaking this down. How can I start simplifying?
On the numerator, you can start pulling all of them apart.
Good. Here's one shortcut that I'll offer you. I have absolute value, right? So what is that going to do to my alternating terms?
I'll get rid of them.
It's just going to make them all 1. So I'm going to start there. And in the meantime, I'm expand the rest of these brackets out. So I have x to the 2n plus 2 over 2 to the 2n plus 2 times this factorial squared over x to the 2n over 2 to the 2n times n factorial squared. And I think the suggestion I got before was start pulling apart these exponents. Since we've done that a few times, here's something I'm going to do. How about I'm going to put something down and you let me know if this needs more clarification. X squared over 2 squared and I'll leave the factorials alone for now. Just do one piece at a time. And now I'd really like to get rid of this compound fraction stuff. All right, let me pause there for a second. Are we okay with that? Okay, let's go ahead and keep simplifying. All right, so getting rid of that factorial will hopefully make this finally possible to evaluate. All right, can I evaluate this limit now? Or would it look a little easier if I pulled out that x squared? I'm going to take the absolute value off because squaring will always make something positive.
Would it go towards 0?
Yeah, it's going to go towards 0. So this limit goes towards 0. So what does that mean about the values of x that are going to make this power series converge? So basically this comes out to be this x squared times 0. So is there any x value I could have that is going to make this limit greater than 1?
No.
No. So what values of x is this series going to converge for?
Any values?
All, yeah, basically all real numbers. So now we have basically seen all the different scenarios for power series and their convergence. So basically one of 3 things can happen here. So if you have a power series that has this form, and I think the first form I showed you was I just had x to the power of n, but really I can offset a power series so that it's not centered around 0, but it's centered around some other number, some number a. So here's one situation. This power series might converge only when x is equal to a. And really that's kind of a really uninteresting case. So basically your power series the only term it has in it that's not 0 is 1. So that's kind of your worst case scenario when, yeah, the only time your series converges is if x is equal to whatever that center value is. Or like the one we just saw, it converges for all values of x. So actually, I think I have this bullet in here. Or you have this thing right here. And this idea is called the radius of convergence. Where basically, this is kind of the middle ground between the 2 extremes. Instead of converging for only one value of x, or converging for all the values of x, it'll converge for only the values of x that are like within this radius of that center value. And this is this is the one where we had to kind of deal with the endpoints. So for that radius convergence, notice these inequalities here. I know that if I'm inside that radius, I converge. I know that if I'm outside that radius, I diverge. But I still have to analyze what happens at the boundary individually. So, and I want to repeat that again. You still have to analyze what happens, basically what's going on here. So you need to analyze this separately. So any questions about those 3 possibilities? All right, so now let's look at this interval of convergence here. All right, so how do we start?
Perform the ratio test.
Good, so we're doing ratio test. So -3 to the n plus 1 times x to the n plus 1 over the square root of n plus 2. All right, got the ratio test set up. Now what?
Break up the top.
Yeah, so all of the n plus 1 side of this, I can break this up. So I get -3 to the n times -3. So that was nice because a lot of these things cancel. And now what I'm left with is this. Absolute value of -3 is simply 3. But I'm going to leave the absolute values in because that x is, we don't know for sure that that's positive. So absolute value of 3x times radical n plus 1 over n plus 2. I'm going to go ahead and pull out the x because the limit has nothing to do with that. So do we know what this limit is going to be?
Would it be 3?
Yep, the limit is 3. So now what I have is absolute value of x times 3 is less than 1. Because really, just a reminder here, I really need my ratio to be less than 1. So now what I have is this equation. 3 times the absolute value of x is less than 1, which means the absolute value of x is less than a third. So this right here, and I'll go ahead and pull this up to the top. The absolute value of x is less than a third. That means my r, or my radius of convergence, r is equal to 1/3. So basically, I already know this for sure. When x is strictly between -1/3 and 1/3, this series converges. So what do I need to do now to finish analyzing this?
You plug in x to this, or plug in -1/3 and 1/3 to the series.
Right. So now we need to evaluate what happens at the ends of this interval. So if x is equal to -1/3, then the series I care about is this. -3 to the n times -1/3 to the n over radical n plus 1. This numerator here will simplify to, basically those are both raised to the power of n, so I can multiply their bases together. That just becomes 1 to the n over radical n plus 1, or 1 over radical n plus 1. What does that series do?
Go to 0.
Well, the sequence goes to 0, but what does the series do?
Go to infinity.
Yeah, it's going to diverge. And that diverges by P series. Or really comparison with the P series, but diverges. So now we have, let's look at what happens when x equals a third. And the series I'm looking at is, here's 3 to the n times 1/3 to the n. And I can still multiply those bases together, but in this case, I'm going to get -1 to the n over the square root of n plus 1. What does this series do? And hopefully see this one converges by alternating series test. So what does that mean for my interval of convergence? What values of x are going to have that are going to make this series converge? So we cannot include -1/3, but we do include +1/3. So your interval convergence is this. -1/3 is less than x, which is less than or equal to +1/3. Any questions here? All right, we got one more. All right, last one. So let's find the interval of convergence of this series. Got plenty of time to do this one. So like before, we're going to use the ratio test. All right, so if we start simplifying, I'm going to have, so the n plus 1 over n, those are not going to cancel out nicely. But I'm going to be left with only 1 power of x plus 2. I'm going to be left with, oh, this is going to be 3n plus 1. I'm going to be left with only 1 power of 3. Here the n remains, but nothing else. And this is going to be 1. And just to make this easier to look at, let's pull out the absolute value of x plus 2. And what is this limit going to be?
One-third.
1/3. So now what I have is 1/3 times the quantity absolute value of x plus 2 is less than 1. So let's first, I want to find this. What's my radius of convergence going to be? What is that constant going to be? So, and basically from there, to find that out, I'm just going to isolate the absolute value of x plus 2, and it's going to be less than 3. So basically, I'm going to, whatever my center value is, in this case, it's going to be -2. Anything within 3 of that center value, my power series is going to converge for. So now let's keep building this up. -3 is less than x plus 2, which is less than 3. So then I get -5, which is less than x, which is less than 1. So my interval of convergence is going to be, you know, so far everything I've shown you, -5 is less than x, which is less than 1. Everything on that interval is going to converge. But now what I have to do is see what happens when x is equal to each of those endpoints. So when x is equal to -5, I have this series. N times -3 to the n over 3 to the n plus 1. So might not be obvious how to simplify this. So one thing I'll do here is break apart that -3 to the n into 2 smaller pieces. So n times 3 to the n times -1 to the n over 3 to the n times 3. That cancels. So what I have left is this. -1 to the n times n over 3. What is that series going to do? So because of that n in the denominator or the numerator, this is going to diverge. And really, that's going to fail the divergence test right away. So we can't include -5. What about +1? So I have n times 3 to the n over 3 to the n plus 1. And what's going to cancel this time? I'm going to have n over 3. And that is going to also diverge by the divergence test. That's going to go to infinity without bound. So really my interval is this. I do not get to include either one of the endpoints. So it only converges for x values between -5 and +1. So any questions on that? All right, I think that's where we'll stop for now. So I'm going to let you go. If you want to stay on and ask me some questions for a few minutes, I'll stay on. I'm going to post the quiz shortly. Otherwise, I'll see you tomorrow.